So here we go again with this idea of plate tectonics. It revolutionized the science of geology. And in 1963, nobody accepted it, of course, as you might expect. But in fact, slowly through the 1970s into the 1980s, everybody accepted it by then. And it was like, almost everybody accepted it by then. And there's still people who think the Earth is flat, right? So it is not flat, but in fact, it is revolving around the sun, and in fact, it is very dynamic as well. And so what you see in this image, we're starting off with what it looks like to be at a subduction zone. Now remember, if you will, there were two types of subduction, right? So there's type 1 subduction. That's what this is. That's an ocean plate being overridden by a continental plate. And it's one in which you actually generate magmas where that subducting slab, some of the sediment, gets drawn down into the mantle and it begins to melt in that setting. And it's charged with water and a few other things, and it comes back. And these magma chambers rise up through the crust then and punch through a little bit back beyond that the subduction zone itself. And so a good thing to think about with something like this is the Pacific Northwest, and in fact the Klamath Mountains that range all the way from southern British Columbia all the way down into northern California. They're volcanic in origin, and that's what you get when you have subduction of an ocean plate below a continent like this. And so you can get a variety of different like magma compositions. So you can go everywhere from intermediate all the way into felsic compositions. So you don't get a lot of mafic intrusions from this, but you do get some, okay? So you get a variety of different things. So that's all within the crust itself where you get that sort of differentiation. But here you can see the lithosphere, in fact, so that is the crust, is just the very top up there, that the purple line that runs across the top of that ocean plate. And then below that is that subcrustal upper mantle. But together they make the lithosphere, and that's being overridden by this continental plate here. That's one of the dynamic interactions you can get when two plates collide. And so those collisions, we can kind of make a short list of how they work. You can have an ocean that collides with a continent, and you get type 1 subduction. You could have a continent that collides with a continent, and that's where you get type 2 subduction. And one continent has a tendency to override the other continent. Or there's some pretty much incredible dynamics that go on there as well. That's what's going on, in fact, in India. So the Himalayas are a result of type 2 subduction, where the Eurasian plate is overriding the Indian subcontinent plate. And so that plate is crashing into the South Asian plate. And what it does, in fact, it squeezes out some of those rocks that were in Southeast Asia. And so you get all of Southeast Asia as a part of what we call escape tectonics. It's a whole series of mountain ranges crumpling, if you will, from that collision with the subcontinent of India colliding. So with this, there's a few designations. The ocean trench is a physiographic feature. In other words, it's just a deep trough that runs along the front of the continent there, and it's where the ocean is actually being subducted underneath of the continent. The ocean crust, it shows you down here, and then it shows you the subcrustal upper mantle below that. It shows you this accretionary prism, and so there's sediments that are shed from the continent, but also scraped off of the ocean floor to accrete onto the continent then. So that's this thing they call an accretionary prism right there, or an accretionary wedge is another term that some people use. And then these rising diapirs, those are the magmas rising up through the mantle to begin with, and then through the crust. And then they show you on here the crustal part of the continental lithosphere, and that's the moho on here. And so if you get down far enough into this, you get all the way down to the asthenosphere. So the very base of the subcrustal upper mantle there constitutes the top of the asthenosphere, essentially. And that's a zone of partial melting too, right? So that shows you pretty much everything that's on here. And of course, it's almost all solid except for the partial melting that occurs in between the asthenosphere and the base of the subcrustal upper mantle there. Here's another diagram that shows you the same thing happening, but it explains a little bit more about the depression of the temperature, the geothermal gradient in a subduction zone. It tells you some of the processes that are going on here. You dehydrate the crustal slab, and that helps by having a little bit of water in there. It helps things go into melt, and so there's a high specific heat with water, and it helps the rocks to melt a little bit. And so you get these blobs of material. They call them diapirs in the last diagram there. These diapirs are rising magma bodies essentially, and they rise up to a point where they're either reach their neutral buoyancy or they begin to differentiate, and then they may become lighter through time, and they may rise higher then in the volcanic and sourcing then the volcanoes up at the very top up then. So that is another diagram that shows this sort of process of subduction. We already know that subduction is a major constituent of the plate tectonic theory. Okay, so it's been tested many times and it's been shown to be right. We get this interaction at the Earth's surface, not just subduction, but we also get spreading centers. That's what's happening in the mid-ocean ridge. That's what's happening a little bit south of Iceland here. They show you a vignette at the very top up here. On the upper right-hand side, you can see the mid-Atlantic ridge there. The two sides of it heading in opposite directions. So the North American plate is off to the left, the Eurasian plate off to the right there, and in between, new crustal material is being added to that mid-continent ridge there in that spreading center. So new crustal material is being added there, and the ocean's getting wider. In fact, it gets wider and wider and wider. Well, it's pushing the rest of the North American continent off to the west there. The only two places where subduction is going on the Atlantic side of the ocean here is along the leading edge of the Caribbean plate, and then also down here at the very bottom, there's one called the Scotia plate. So there's actually subduction going on under those. But notice also when you jump over to the Pacific plate over here, the Pacific plate also has a ridge in it where new crustal material is being added, but it's not quite so rapid. And that's over here on the west side of the Nazca plate, and that's the Pacific plate on the east side then. And so that's where new crustal material is being added there. And there's actually new crustal material being added between the Nazca plate and the Cocos plate here. And then both of those are being subducted under Central America and South America. And you get volcanoes there, of course. And so Central America volcanoes, famous south part of Mexico as well. Huge volcanoes there, larger than anything that we see in the rest of North America. And so until you get up into Canada and into Alaska. And so there's some big mountains up there as well. But here in the South American plate, up to 22,000 feet high, some of the volcanic mountains there. So what you're looking at here is subduction over on the upper left-hand side. You're looking at a hot spot in the middle part there. That's underneath Yellowstone, where the North American plate has overridden a hot spot, it seems. And you get the Yellowstone volcanics, and there's a track that actually leads back across southern Idaho all the way into Oregon and across part of Nevada as well. You can track where that hot spot has been overridden for at least 15 million years or more. And so on the upper right, then you get the spreading center. On the lower right, you see a rift zone there. We've kind of talked about this already. So a rift zone is another type of divergent plate boundary. Divergent meaning two plates are heading in opposite directions. So that's East Africa rift zone there. And up at the top, of course, it's the Atlantic mid-ocean ridge that has North America going one way and Europe heading the other way, the Eurasian plate heading the other way. At the bottom down here, you can see a continent overriding in that subduction zone here, you can see a continent overriding the ocean plate that is the Nazca plate there. So that's the vignette in the middle at the bottom there. So just to be clear, up in the upper left-hand side, that's an ocean plate and an ocean plate there. So that is the Aleutian Arc, which is partially an ocean plate overriding an ocean plate. And so in that one, you still get volcanics, right? And so, but it's just a permutation of these sort of collisions that you get. So that is a convergent plate boundary. The one in South America in the middle at the bottom down here, that's a convergent plate boundary. And then, of course, the other hotspot example that they give on here is the Hawaiian volcanic chain, okay, that goes on with the Emperor Seamounts. So that is pretty much the different varieties of interactions that you get with plates. It's a continent-continent collision. You can get that at a convergent plate boundary. You can have an ocean-continent collision where the continent overrides the ocean. That's what happens in the Pacific Northwest, where the Juan de Fuca plate is shown on here. Also in the Nazca plate down here. And then you can have ocean-ocean colliding. That's the Aleutians on here, and another convergent plate boundary. And then you have the divergent plate boundaries like the mid-ocean spreading center and then the East Africa Rift Zone. They can also be static, by the way, so they can stick together sometimes and not move relative to one another. So that's called a static plate boundary. And then sometimes they can have long faults that go side by side where they just kind of slip by one another with very few volcanics, as it turns out, but lots of earthquakes. That's what's happening in the southern part of California. So below the Klamath Mountains, below the northern part of or southern part of the Klamath there, and some of the volcanics in northern California, you get side by side. So that's the San Andreas Fault as an example of that type of plate boundary. It's a translational plate boundary, and you get strike-slip faults there. So those are the main varieties of plate interactions that we see on this planet: divergent, convergent, translational movements side by side, or static. Okay, so 4 different types of plate boundaries then. So you already know that the continents are absolutely ancient. Some of the oldest rocks that we have are from continents. That's up to 4 billion years old, right? The ocean plates, in contrast, are really, really young. And in fact, they're yesterday when you're right at the spreading centers, right? So, or today even. And so at the spreading centers, new crustal material is being added there. Well, then what's the oldest continental ocean crust, right? So the oldest ocean crust, as it turns out, is only about 190 million years old. I say only. I mean, I'm a geologist, right? So that comparing that to 4 billion years old on the continents, that's quite a difference. In fact, when the dinosaurs were roaming around on this planet, that's about roughly the same age as the oldest ocean crust. And you see it in this diagram with the blue spots on here. So the blue areas are the oldest ocean crust. The youngest areas are the hottest also, and that's where you get the reds and the oranges and the mid-ocean ridges that are actually drawn on this diagram as well. So if all of those continents were once together, you can kind of see how this whole thing would have split apart through time. And it's only been recently. I'll try to include it actually on here, but there's a new movie that shows that animation about how the continents more or less split apart over the last 500 million years. This has just been the last 190 million years that we have this configuration for oceans and continents on this planet. What it means is we have a dynamic planet, and things are going to change in the future too. So there's going to be some change going on here. Eventually, we're going to get some subduction really being more pervasive in the Atlantic at some point, and we eventually will form another supercontinent, and probably on the Atlantic side as opposed to the Pacific side. That's the projection anyway. So when we have all of this sort of plate activity, when things are breaking apart around old ancient plates that are now, for instance, all of the various plates that make up Eurasia, there's got to be about 30 of them in there. But the Siberian platform is one of those. There's the East European platform. There's the Scandinavian platform. All of the Baltica, they called it at one time, right? All of those things are little tiny continental fragments that have been amassed together in the giant continent of Eurasia today. At times, those things have tried to split apart as well. And so, for instance, roughly about the same time as the extinction of the dinosaurs, in India, there was a massive outpouring of lava. And so these things are where continents try to have some sort of splitting apart or some sort of activity. And in fact, you get these massive eruptions. And in fact, we've talked about them already. This is where the steppes are. And so the Siberian, the traps, that's the Swedish word for steppes, are the traps. And so the trappa are in the Siberian area there, and the Deccan traps down here in India. And so those two areas have had massive outpourings of lava. Well, they're not the only two on Earth. There's the Central Atlantic mafic province that you see on here as well. That's Camp on here. And then there's the North Atlantic igneous province as well. That's around Iceland there, and including Iceland, you can see here. And then there's the Kerguelen Islands that I mentioned previously with the mantle volcanics. Well, it's a hot spot underneath of that. And there's a huge there has been a huge outflowing of magmas at one time. There's one at the Karoo. There's all these various places, the Piranha, all of these places across the world that have had these huge outpourings of lava. Most of them have been mafic, in fact. There's even one in North America. You can see it. It's the Columbia River Plateau basalts. And so if you ever get a chance to go to the eastern part of the state of Washington, or if you go to eastern Oregon, or if you go to the western part of Idaho, you'll see the Columbia River Plateau basalts there. Really pretty amazing sort of accumulation of basalts where the earth just opened up and it flowed out. Well, those are around some places that have had either subduction going on, or there's been some sort of rifting event that has stopped for the time being, or it's at least slowed down. So, for instance, at the Afar Triangle is one of those. And so that's in northeast Africa there. Okay, as we go on, we know that the continents are much, much older than the ocean crust. And in fact, the continents are made out of tiny pieces of older continents. In fact, those older continents sometimes get herded together in forming these larger continents. And so in North America, for instance, there are about 5 or 6 different smaller continents that came together to form North America. When we talk about the core of a continent, we're actually calling that the Craton. So a Craton, it means strength in Greek. It's called Kratos or Kratos, and it means strength, but that's the older, stable, structural part of the North American continent, for instance. So we have a Craton that is partially exposed even today, in fact. And so where it's exposed, we call it a shield. And so that's the Canadian shield today in North America. We also have a Greenland shield, in fact, but it's mostly covered with ice. And so the Greenland shield and the Canadian shield together form the core of the North American continent. In places, so the shields are where that's exposed. And so the glaciers have come along and scraped off all the sedimentary rocks, in other words, and you get right down to the core of the continent below that. And that's going to be igneous and metamorphic rock in that setting, and maybe some ancient ocean crust that got squeezed in between those microcontinents that dock together. Where sedimentary rock has been deposited over the Craton, we call that the platform. So if the sedimentary rocks have been scraped off of the shield part of a Craton, the part that's still underneath or partially buried by sedimentary rocks, like in Missouri, we have about 1,800 feet right here in Springfield that's been covered by continents. Those sort of areas we call the platforms. And so the platforms are these areas that are Craton covered by sedimentary rock or sediments. And in fact, there's a few places where North America has collided with island arcs and you form mountain belts. And even back when North America collided with Africa and collided with Asia, we formed the Appalachian Mountains in the eastern part of the United States and on into maritime Canada. So the Appalachians, these events are called orogens, orogeny. So oro means mountain, and how they began is the origin. That's what that means. And so the origin itself, or that rock body that would have been from the collision of two continents that collided together. So the Appalachians share something in common with the Himalayas. They're just not quite as high as they are. And at one point, it broke apart, and Africa went one way, Asia, Eurasian plate went another way, and North America is heading to the southwest today. And so those are called origins, these mountain belts that form from the collision of continents, or island arcs. You know what a platform is, you know what a shield is now, and a basin. A basin is actually a feature that develops on a platform where it's relatively thick sediment that gets deposited there. Over 1 kilometer thick, in fact, is the cutoff we use for that. So those are the parts of the continent itself. You can get the shields, you can get the platforms, you can get the origins, you can get these basins. And basins are really important, in fact, for the mineral resources that they have and also the energy resources. So basins are invariably associated with oil and gas or with coal resources. And so that's why basins are really important on the continents themselves and actually around the periphery of the continents, on the continental shelves and so forth. So if we look at the various parts of the Earth, this shows you where the origins are in a sort of aqua blue there. You can see where the deep basins are in the sort of like natural blue on the continents themselves. They just show you the ocean floor. They don't show you, but this is actually differentiating the parts of the continents themselves. In the pink here, you can see the platforms and you can see the shields in the orange then, and then the large igneous provinces show up as the purple on here. And so that's from the U.S. Geological Survey. And they show you some of the crustal ages on here as well. So the shields have a tendency to be really, really ancient parts of the crust. And in fact, that's where we find some of the oldest rocks on Earth, 4 billion years in North America. Here's a close-up of the North American Craton. And part of that's covered with sedimentary rock. So don't think that that's all exposed igneous and metamorphic rock. It's not today, because there are places that are covered up with sedimentary rock and sediments as well. But it shows the mountain belts. And so that's these areas that are called the deformed craton on there around the periphery of the craton. And then also you get these sort of mountain belts like where the Appalachians are. And then there's a coastal plain out beyond that. So if we were to look at more detail of the map on the left-hand side and look at it on the right-hand side, it actually shows you what some of these older parts of the Craton are made out of. So for instance, in Missouri, we are a part of what's called the Yavapai Mosetsol terrain. And so that's where the Yavapai and the Mosetsol continents have collided, or arcs have collided with the rest of the North American continent. And so that would include the Wyoming Craton. It's the Superior, well, they call these provinces, the Wyoming Province, the Superior Province, the Nain Province, the Ray Province, and the Hearn Province. All of those have come together to form the core of the Canadian Shield, that is that main part where it's exposed today. And in fact, part of that's been covered over by platform sediments as well. And so the continents are absolutely ancient in age. So that takes us to the very end of plate tectonics and this summary. When we talk about plate tectonics, it's the dynamics and the interaction of plates with one another that really kind of define plate tectonics. It's where we get subduction. It's where we get mountain ranges. It's where we have huge outpourings of lava sometimes. These sort of things happen at those boundaries or within continents where eventually it could turn into one of those boundaries. So the East Africa Rift Zone, for instance. Volcanoes are found at most at some plate boundaries. Let me put it that way. At the convergent plate boundaries, like the ocean-ocean subduction zones, you get volcanoes there. Where the oceans collide with continents, you get subduction. You have volcanoes there. Where the continents collide with one another, it's less common to get volcanoes there. So that's like the Himalayas. And in fact, in the Appalachians, they don't find a lot of volcanic rock directly in the Appalachians. You had to break it apart in order to get volcanic rocks there. And so that's off to the east, in some rift zones that developed in the eastern part of the Appalachian provinces. So those are the places that you get volcanoes. And so the hot spots also, of course. And so you can get hot spots underneath continents, or you can get them under the ocean plates as well. So earthquakes are common along faults, and every one of these boundaries is susceptible for earthquake activity. So seismic events are going to happen in those sort of places. They happen less likely in the continental interiors, but they still can happen there as long as you have some sort of boundary there that's been active in the past, or it's active today perhaps. So even in Missouri, we have an active sort of boundary in the New Madrid Fault Zone. So we get earthquakes even in southeast Missouri and a few other places, but they're really small ones anywhere else in Missouri. But the ones in the eastern part of Missouri can potentially be very, very active. And you wouldn't think it, but there are places along the Atlantic coast that can have a lot of activity as well. There was an earthquake in New York not too long ago. There was one in Virginia that was like a 5 point something. There was one also, you wouldn't think this would be a seismically active area, but in South Carolina around Charleston, that's another place where there's some seismic activity as well. They happen along faults. And so these faults are really common along plate tectonic boundaries, but not invariably, because so you can get faults in the rest of the continent as well. In fact, we have faults that run right through Springfield today, and they affect the sediments that are here, or the sedimentary rocks that were deposited over the Craton here. So with these tectonic plates, we're talking about the crust and the subcrustal upper mantle. So it's crust and scum. That's the acronym we use, subcrustal upper mantle, SCUM. So crust and scum form these tectonic plates, and those float around on that zone of partial melting at the top of the asthenosphere. So the plates are actually part crust and part upper mantle, subcrustal upper mantle. And so that acts together as these tectonic plates. And there's the things that interact with one another. They give us the mountain ranges. It gives us the rift zones, the spreading centers, and so forth. So with earthquakes, they can occur all the way down to 600 meters. And we're going to look at this in a little bit more detail when we talk about earthquakes. But the folks who found that was a Japanese fellow named Wadati, Dr. Wadati, and then Dr. Benioff, who's an American actually. And so between the two of them, they call it the Wadati-Benioff zone, but you can get earthquakes up to 600 kilometers deep. And that's kind of, it's the ones nearer the surface that actually pose a bigger problem. If it's 600 kilometers deep, it's going to be kind of muffled by all the crustal material that's over the top. So they're not quite as dangerous then. The crust itself is 0 to 70 kilometers thick, and you now know some of those other boundary elevations as well. The base of the crust is identified by the moho, of course, and if you get down to 70 kilometers, you're going to see the moho there. Okay, in Missouri, you're going to see it at about 42 kilometers or 44 kilometers thick in Missouri. Below that, you get the subcrustal upper mantle. Below the subcrustal upper mantle, you get that zone of partial melting. That's the upper 250 kilometers then that form the plates. And then you have to go down to 600 kilometers to get to the base of the asthenosphere before you finally get to the lower part of the mantle. And so that lower part of the mantle, they have a subdivision in it as well. That D double prime layer is right at the core mantle boundary and may be the source for those mantle plumes that rise up. And beyond that, below that, in fact, you get this molten outer core that revolves around the inner core that gives us our magnetic field. And the inner core is solid and has two different layers in it as well, but they're both solid. And so that's the inner core and the outer inner core, but the outer core itself, liquid. The outer core is liquid. And that pretty much covers the aspects of plate tectonics that we're going to cover in this presentation. We're going to see this again when we talk about earthquakes, and we'll talk a little bit more about seismic, I think, at one point in here when we talk about petroleum resources and things like that. But for now, that is the end of the second presentation on plate tectonics. Thank you for your attention. This should constitute, actually, previously I misstated myself, this should be the end of all the materials that we cover before the exam, which will be a week from today. And so that's enough material to watch or listen to, however you do it. But anyway, that's it for the midterm, essentially. So our midterm exam, even though the midterm grades have to be turned in on Wednesday, our exam is going to be on Friday. So your exam won't be part of the midterm grade. I'll take what you've accumulated so far, and make adjustments for those of you who've been sick and so forth or in quarantine. And that's what's going to be reported for the midterm grade. So don't sweat it too much, I would say. And I will see you, as they say, on the flip side here, and we will talk again after spring break. And so this will be pretty much the last of the video presentations that will be offered before the spring break. And so there'll be a new set for after spring break. And I probably won't post those until during spring break. So don't worry about them, I guess is what I would say. What I would worry about if I was you is that you have an opportunity to come to a review on Wednesday. So that's going to be the 10th. Wednesday the 10th, we will have a review during regular class time, which if you didn't remember what that is, that's at 10:10 a.m. And I will be available for you to ask questions of all the way up till 11 o'clock, and then I got to head out. So, but 11 o'clock on, between 10 and 11 on Wednesday, I'll be around. You can come in, you can ask your questions, and I'll try to give you a hint about what's going to be on this exam. We've covered a fair amount of material, but we've also had some snow days and things like that as well. So it's kind of slowed down our progress a little bit in that middle part. But I think we're pretty much on track in this course otherwise. So anyway, I'll let it go with that. Thanks a lot for your attention, and I will see you soon. Thanks. Bye now.